Hello, my name is Eric Stromberg. I'm the Division Director of the Space Systems Division here at Atmospheric and Space Technology Research Associates, and today I'm going to be talking to you about our SORTIE 6U CubeSat mission. SORTIE stands for Scintillation, Observations, and Response of the Ionosphere to Electrodynamics. And today we're going to be talking a little bit about the first light data that we've received since being deployed from the International Space Station earlier this year. I'd like to thank my co-authors on this paper and presentation, as well as the Small Satellite Conference for allowing us to perform these presentations virtually. A little bit about ASTRA. ASTRA is built on 5 fundamental pillars, from modeling and data assimilation to data and engineering services, ground-based instrumentation development, and our Space Systems Division. In our Space Systems Division, we participate in full missions, such as the SORTIE mission that we'll talk about today, as well as instrumentation development, data and engineering services, mission operations, and participation on science teams. And what that allows us to do is continue to work on advancing the current state of the art for technology and science research. And participate in a multitude of teams with a number of partners. We're currently celebrating our 15th anniversary, and we're very excited about the work we've been able to do so far, and excited about what the future holds for us. Early last year, we were able to form a joint venture with Pumpkin Space called Orion Space Solutions, and what that allows us to do is an end-to-end space mission solution provider, all the way from mission design and planning to spacecraft and subsystem development and implementation, payload design and interfacing, performing analysis, integration, test, and calibration, and then our mission operations. And so what that allows us to do is perform really that end-to-end service capability from taking an idea, designing a mission to be able to fulfill that idea and need, and then all the way through implementation and mission operations on the backside. So a little bit about SORTIE. As I mentioned, SORTIE is a 6U CubeSat mission sponsored by NASA. We have partners with AFRL, University of Texas, Dallas, and Boston College. We were launched in December of 2019, and that happened to overlap with the NASA ICON mission. And what that allows us to do is perform comparisons between SORTIE's mission data and ICON's data and be able to examine what the phenomenology looks like between the two instrument packages. We're currently in science campaign mode and performing nominal operations there. And we've got a year baseline non-orbit lifetime requirement so that we can get the full season variability of what we're studying and the phenomena we're looking at. And we have a little bit of margin built into that, as we'll talk about later in this presentation here. So the science objectives for SORTIE, we're really interested in studying wave-like plasma perturbations in the ionosphere. Now, these perturbations can be caused by both man-made and non-man-made phenomena. And so we want to understand what the relative dynamo action is, and understanding how these wave-like perturbations are formed and how they travel through the ionosphere. And here's a comparison of some of these waves that have been observed by the CONOPS data. The reason why this is so important is shown on the slide here, where the two images on the bottom are separated by about 3 hours in time. And what you can see from the arrows is that not only in those 3 hours have the waves shifted direction, but they've also changed in amplitude and structure. And so really we want to understand what's going on in the formation and the phenomenology that causes these perturbations and how they move through the ionosphere, because what that does is that tells us a little bit about what the ionosphere is doing at that particular point in time. The goal would be to be able to fly a constellation or a number of these SORTIE spacecraft to be able to allow us to create a global atlas of what's going on in the ionosphere, and be able to study where these perturbations or how these perturbations travel around the Earth. So a little bit about the spacecraft. So ASTRA was in charge of performing all the integration and testing and calibration, working with our partners from UTD, who provided the IVM instrument package, and we'll talk about that in a minute. And AFRL, which provided our PLP instrument package. We worked very closely under our JV with Pumpkin for some of our power components, our batteries and our solar panels. And again, ASTRA performed all the integration, testing, and design of the spacecraft itself, as well as the onboard computer. Our antenna system and our communication system is using cadet radio, and so we use a single monopole deployable whip antenna to be able to perform that communication aspect. The nominal operations for the CONOPS overview is basically we want to perform observations between the plus and minus 30 degrees latitude, and what that allows us to do is be able to examine the entire magnetic equator, especially as it dips due to the South American anomaly or something similar. And so we want to basically make sure that we are performing our nominal observations between this plus and minus 30 degrees latitude, which allows us to downlink data when we're outside of that region as well as perform other items such as torque rod, momentum dumping, which in the end impact some of our measurements. And so that's really kind of the band that we want to operate in. The instrumentation packages, as I said, the IVM was provided by University of Texas at Dallas, and this is based on a number of instrumentation packages that they've developed over the years. And so this is kind of a miniaturized version of that, and some of the specs are shown in the top left there. The planar Langmuir probe, shown on the bottom right, was provided by AFRL, and basically between the two instrumentation packages, between the ion velocity meter and the planar Langmuir probe, we're able to provide a snapshot of what's going on in the plasma as we fly through it. Both these instruments are oriented in the ram pointed face of the spacecraft, and so as we fly through the plasma and through the velocity vector in the plasma, we're able to collect ions and understand what's going on. As I said, for the mission operations, we're using the Cadet U radio from L3 Communications, and so we're utilizing the NASA ground station at Wallops Flight Facility. All the mission operations is being run out of ASTRA's Mission Operations Center, and again, we've been operational since our deployment from the International Space Station earlier this year. For the lifetime, right now, again, we're shooting for that requirement of about a year of lifetime, and that allows us to get that seasonal variations and seasonal variability that happens in the ionosphere due to being closer and farther away from the sun. And so out of that 1 year nominal lifetime, we ended up adding a little bit of ballast mass to our spacecraft, taking us from about 7 kilograms to just over 11 kilograms. And so that gives us plenty of margin on our lifetime to be able to make sure that we get that full season variability and understand what's going on. So SORTIE was delivered on September 30th to NanoRacks for integration into the dispenser. So we transported it down to NanoRacks' facility in Houston. From there, it was integrated into the canister and then moved to the launch integrators and the payload managers for the resupply missions. And I do want to do a big thanks to the NanoRacks crew for all the support that was provided for our integration and delivery. We're very happy working with them and excited about our next opportunity together. So these are just some snapshots in the next couple of slides about our delivery, launch, and deployment. So this slide overviews the loading into the dispenser, performing final checks, and then on the right side there you can see that it was delivered from NanoRacks facility to Leidos for the cargo mission managers and be able to load into the manifest essentially for the launch. SORTIE was launched aboard the CRS-19 mission, the SpaceX resupply mission, on December 5th, 2019 out of the Cape. We were one of several CubeSat missions on this ride as part of NanoRacks' 17th deployment mission. And these are some great shots of the launch from the Cape. SORTIE was deployed from the International Space Station on February 19th at about 1740 GMT, and you can see in the picture on the lower left there is the canisters from NanoRacks being loaded into the airlock and then being deployed out into space. So you can see on the right side there's a great shot of it coming out of the canister and going into orbit. So SORTIE's been gathering data since its orbit insertion in February of 2020. We've been performing early checkout and satellite commissioning, and that's been completed. And so we're now into our nominal operation modes, and it's been operating as expected, and we're very excited about the data sets that we have. The example picture that's shown here is some of our temperature plots. So basically evaluating what the temperature looks like of the spacecraft as we fly through in our ISS type orbit. And we've been very happy with the results so far for the temperatures. They've been about where we were predicting them pre-launch. So some of our first flight data for the IVM, which is what we'll talk about on the next couple of slides. This is really the first demonstration of a single aperture ion velocity meter, and we've been very happy with the results that have come out of this so far. The measurements that we've been able to see appear to be very robust and across the whole data segment, all the way down to measuring a couple of picoamps. So again, we're very excited about the performance of the instrumentation packages. And the plots on the right there show a little bit about the current coming into the instrument and then the arrival angle, both of which are high resolution images, and so we're very excited about the resolution that we've been able to achieve on our measurements so far. Moving into level 2 and actually looking at density and composition essentially. So this circular orbit at 420 kilometers, we've been able to look at ion composition as well as the temperature and then the ion drift, essentially. And as the bottom bullet points out there, the first light results demonstrate that really these ionospheric science measurements are possible using these CubeSat missions. And so again, we're very excited about the miniaturization of the technology, the demonstration of essentially everything we've been able to prove so far on the mission, and we're very excited about what we're going to be able to achieve kind of over the next year or so. So looking at ion temperature, so we perform a number of operations to improve the data performance, essentially coming out of the instrument for the IVM. So the top right plot there shows essentially the raw data set overlaid on top of each other, and then we perform an average and then some binning that happens, and basically what we get is we get one average local time per day, calendar day, essentially, for our line as we go through. And so what that allows us to do is be able to eliminate some of the noise and some of the outliers that exist in the data sets, and it allows us to do some comparisons between our data and the ICON data. So for the ion temperature and comparing it to ICON, so we talked a little bit about that on the last slide. So there's different orbits between the platforms, and so there's some variability that's expected between the two instrumentation packages. What's shown on the plots on the bottom there are essentially a single day for ICON, and so you're getting a curve per orbit, and it's multiple days of SORTIE, which is a curve per day. And you can see that there are some densities that agree pretty closely to SORTIE. And what we've been able to show is that the SORTIE IVM package is actually very clearly producing geophysical temperatures and observing geophysical phenomena. And so again, we're very excited about the results that have come off this so far. For the composition measurement, so this is an example of some of the oxygen ion fraction results and the composition that happens in the ionosphere that we've been able to measure. So you can see that there is some structures that are built into it. The data gaps are in the middle there are essentially early operations, and so as we move through our operation package, we're planning on being able to get a little bit more granularity and a little higher resolution in the data sets. But we've been very impressed with what we've been able to see, and we can actually very clearly see some structures that are built into the density and the composition. So for the density results, as I said, again, we can start seeing some of these phenomenologies that exist in drift due to local time, which again is expected, just based on how the ionosphere behaves, and it's something that we've seen quite often in some of our ground-based instrumentation packages. And again, comparing essentially local time from 0 to 24, and then our date essentially from late May to early June. And again, this phenomenology that we're seeing in some of the structures are very promising. So for our RAM drifts, so basically we've been able to do a conversion of measured drifts to a geophysical basis, and that conversion requires incorporation of some of our spacecraft attitude and ephemeris, which is in progress right now. And again, so we're expecting that these results will get better and better over time. And what's shown is total ion velocity into the instrument. And so again, we're on the order of several thousand meters per second entrance velocity into the spacecraft package. Again, there's structures that we can see in the data sets that we do have in some of this early data. And as we continue our science campaigns, we'll be able to look at some more higher fidelity data sets as we move forward through our mission. And with that, I'd like to say thank you. Again, we're very excited with the data sets that we've received so far. And the mission so far has shown extreme promise into developing these ionospheric measurement capabilities from CubeSats. And we are currently working on a number of papers that we're getting ready to publish on the data sets. And so as we continue through this, we look forward to continuing to present data sets from this and potentially coming back next year. Thank you very much, and have a good rest of your day.